In this video, we're going to look at some examples of drawing resonance structures when we're given a particular molecule. What I have here is the cheat sheet from my last video on resonance structures, and these are the patterns that I'm going to be looking for when I'm trying to draw the resonance structures of each of these molecules, and I'll be referring back to each one of these particular patterns. All right. So we're given a molecule, and we want to draw the possible resonance structures for it, or the possible alternate resonance structures for it. And so one thing the book does, and so I've done the same thing here, is they didn't put the lone pairs in on the oxygens and the nitrogens. So we need to be sure that we do that. So they are given the formal charges, right? So if I have a neutral oxygen, it's going to have 2 bonds and 2 lone pairs. So I know that I have 2 lone pairs on that oxygen. And so the only pattern that I see that we have is we have a lone pair that's allylic to a double bond, right? And to be sure that we're in the right distance, remember the rule is 1, 2, 3. So when I start on the double bond, right, I've got 1, 2, 3, right? And so this is a 2-step. And so we're going to take one of our lone pairs, and it's going to form a double bond there. And then this double bond is going to form a lone pair on that carbon atom. And so the resonance structure that we're going to get right, so now we have a double bond here. We have just the single lone pair now on the oxygen. And I made a mistake here. That's not supposed to be an oxygen. That's just going to be my lone pair, right? And now I've got to check that my formal charges in the new structure are correct, right? So the oxygen went from having the lone pair to now sharing that lone pair, so it's going to go from neutral to positive, and then this carbon atom went from having to share those bonded electrons, now it gets them by itself, so it's going to go from neutral to negative. And I think that's the only resonance structure that we have for this particular molecule. Okay, here we have another example, and I think the pattern that I see in this case is I have a carbocation allylic to a double bond. Right, and again, the pattern I'm looking for is 1, 2, 3. So they're close enough to do it. So what's going to happen here is the double bond is going to move over there. This is just a 1-step, or a 1 arrow. All right, now my double bond is here. This guy didn't change. Right, and so this carbon atom went from having a positive charge, right, we added these bonding electrons, so it's going to go from positive to neutral, right? This guy, right, is losing a bond, but it's gaining a bond, so he's not going to change, right? But now this carbon atom is just losing those bonded electrons, so he's going to go from neutral, and now he has our positive charge. Right, and then you can see we can do this again. And now my double bonds are there and there. This is the carbon that lost the bonded electron, so he gets the positive charge. And then that's as far as we can go. Right, I can't go again because now, right, if I tried to move it again, it'd be 1, 2, 3. Right, that's not where the positive charge is. So this positive charge is not allylic. Of course, I could go back the other way, but that's just going to get me the other resonance structures I've already drawn. Okay, here we have another example. And again, they're not putting the lone pairs on the nitrogen, so I should put those in. Right, and when nitrogen is negative, it has 2 bonds and 2 lone pairs. And so I think the pattern that I'm seeing now is I have an atom with a lone pair adjacent to a carbocation. And so these electrons are going to move down here. right? And now my nitrogen atom, right, essentially went from getting the lone pair by itself. Now it's got to share those lone pair, so it's going to go from negative to neutral, right? And my carbon was positive, right? But now it's gaining some bonded electrons, so it's going to go from positive to neutral. All right, again, we should put in our lone pairs. A neutral oxygen has 2 lone pairs. I think the only pattern that we have here is I have atoms connected by a pi bond that have different electronegativities. So we're going to move the pi electrons, put those on the oxygen. All right, now the oxygen went from sharing the electrons to getting in a lone pair, so it's going to go from neutral to negative. And the carbon is losing those bonding electrons, and so it's going to go from neutral to positive. All right, let's put our lone pairs in again. All right, so the first pattern I see is the same one that we had last time. I've got 2 atoms connected by a pi bond with different electronegativities, so I can move those electrons up to the oxygen. And that's going to give me that resonance structure. And now I have a carbocation allylic to a double bond. And so we can find another resonance structure by doing that. So now the double bond is there. Right, and then the one that lost the electron density was that one. Okay, in this case, again, they're not putting the lone pairs in, so we've got to figure those out, right? And when carbon has a negative charge, that means it's going to have a lone pair. All right, and so now I have a lone pair allylic to a double bond, right? Again, our pattern 1, 2, 3. And so I can move those guys down. This is the one that's a 2-step, or 2 arrows in the same step, I guess I should say. So now the double bond is here. The lone pair is here, right? And this carbon, it started out, it got to keep the lone pairs for itself. Now it's got to share them, so it loses the negative charge, right? This guy had been sharing the bonded electrons. Now he gets them by itself, so the negative charge has moved over there. All right, so I think I'm going to start this one off. Well, I guess I should start off by putting on our lone pairs. And one important thing to notice when we're doing these resonance structures is look for all the one arrow ones first. And the reason I say that is there are 2 things we could do here. We could do the 2 atoms connected by a pi bond with different electronegativities and move those guys up, or we could say, oh, hey, we have, right, a 1, 2, 3. We have a lone pair allylic to a double bond, but if I do that one first, I'll only get one other resonance structure. If I do this one first, we're going to find we get 2 additional resonance structures. So if we can do a 1-step before, rather than doing a 2-step, or 2 arrow, we want to do that. And so we're going to do this one first. If we don't do the 1 arrow first, then it's easy to miss some of the resonance structures. All right, and now I have a lone pair adjacent to a carbocation. So we'll do that. And the positive charge moves there. All right, just one more example. Okay, so this last example has quite a bit going on. And so the first time is I'm going to go ahead and draw in my lone pairs. And now I think you maybe see we have 2 different patterns that we've talked about. So I have 1, 2, 3. So I have a lone pair allylic to a pi bond, and I have 1, 2, 3. So I have a carbocation allylic to a pi bond. Now, if I do the resonance structure with the allylic lone pair first, let me draw, right, so I'm not going to draw the arrows, but right, what's going to happen is this lone pair is going to come down and form a pi bond, then the pi bond is going to come and form the lone pair, and my resulting resonance structure put in that oxygen. And so you can see one thing that's happened is I've gone from 1 atom with a non-zero formal charge to 3 atoms with a non-zero formal charge. And this is something that, well, I guess I've left off this other, I didn't finish it off. I need my other pi bonds here. Sorry about that. One thing that we haven't talked about yet that we're going to actually talk about on the very next slide is determining the relative importance of resonance structures. And one of the rules that we have is resonance structures are generally better when fewer atoms have non-zero formal charges. And so if you were to draw this resonance structure, I wouldn't mark it wrong. But after watching the next video, if I asked you to compare the importance of this resonance structure to the other ones that I am going to draw, I would want you to be able to know that those are more important. So this may make more sense after you watch the next video, but I wanted to explain why I'm not going to sort of explore this tree of resonance structures that I get by starting off by forming the resonance structure of this allylic lone pair. So these are not going to be as important as the other ones. They're not necessarily wrong, but they're not going to be as strong of contributors as the ones that I am going to draw. So the tree I am going to focus on is dealing with that allylic carbocation. So the first resonance structure we would get right now, this atom ends up with a positive charge. Okay, and then we can keep moving this guy around the ring. Let me put back in the lone pairs on the oxygen here. We don't need them now, but we will in a minute. All right, so we're going to move that carbocation over another 2 spots. Okay, and I'm out of room here, so we'll go on to the next slide, but I think you'll see, right, I have another space I can move that guy over. Okay, so now up here we're starting with the resonance structure that we left off from last time, and so All right, and then we have one last resonance structure that we can draw. Now I have a lone pair adjacent to a carbocation, so it's a different pattern, but I can move it over one more time. And so those are the most important resonance structures that we can draw for this molecule. And if you were confused about why I didn't draw those other ones, watch that next video and then maybe come back and watch this last example again, or certainly ask me about this in class.